Welcome to a screencast on Molecular Geometry Part 2 and an Introduction to Molecular Polarity. First, a reminder of the information in a previous screencast, and that is the valence shell electron pair repulsion theory, in which electron groups repel each other, get as far apart as possible, and that determines the electron group geometry, which may be the shape of a molecule if all electron groups are bonds to atoms. And a reminder of the electron group geometries: 2 electron groups makes a linear electron group geometry, 3 electron groups makes trigonal planar electron group geometry, 4 electron groups makes a tetrahedral electron group geometry, 5 electron groups makes trigonal bipyramidal electron group geometry, and 6 electron groups makes an octahedral electron group geometry. And again, if all those electron groups are bonds to atoms, then those are the molecular shapes as well. But one or more of the electron groups may be lone pairs, and if that's the case, if they are not a bond to an atom, then the molecular shape is different than the electron group geometry. And that's what we'll take a look at now. And we'll start with 3 electron groups. Here they're shown all as bonds. So this is a trigonal planar electron group geometry. And if all of the atoms or all of the electron groups are bonds to atoms, then that's a trigonal planar molecular shape. But let's suppose one of those electron groups, say the one being pointed at here, is not a bond to an atom, but it's just a lone pair. So here the purple connector represents there's a lone pair of electrons here. That's electron density that repels these electron densities in these 2 bonds. So the electron group geometry is still trigonal planar, but if there's no atom bonded here, then the shape of the molecule is in fact a bent shape. And here's another view of it. So it's just angled or bent. Now we have a 4 electron group geometry, tetrahedral. And again, right now the model is showing all of the electron groups as bonds to atoms. But if one of those electron groups is not a bond to an atom, but it's an electron group that's a lone pair, so again, the purple connector is going to represent that. Here's the top view, and there's a bit of a side view. And again, tetrahedral electron group geometry, but you should be able to see that there's a triangle in terms of the atoms, and it's not planar, it's a pyramid, so we call the molecular shape in this case trigonal pyramidal. Okay, so electron group geometry, tetrahedral. Now, and previously the molecular shape was trigonal pyramidal. So now a second electron group is a lone pair. So we have 4 electron groups still, but 2 are lone pairs, 2 are bond pairs. Still a tetrahedral electron group geometry, but as you can see, the shape of the molecule is now bent. Okay, now we have a trigonal bipyramidal electron group geometry, and the model represents all electron groups being bonds to atoms. And here we're getting a bit of a view from the top, so you can see the trigonal part. And then there's a pyramid on the top and a pyramid on the bottom, so it's trigonal bipyramidal in terms of electron group geometry. And if all of the electron groups are bonds to atoms, then we would have a trigonal bipyramidal molecular shape. But let's say one of those electron groups, this one, and quick note, the electron group, if one of them is a lone pair, it's going to be an equatorial position. So that electron group is a lone pair. So now we've represented it by a purple connector again. It's electron group. It's not connected to an atom. It still is creating the shape of the molecule. It's still part of the electron group geometry. But if that electron group doesn't bond to an atom, we don't have a trigonal bipyramidal. We have a seesaw molecular shape, and there's the side view, seesaw or sawhorse molecular shape. Okay, well, what if one more electron group is a lone pair? And again, this is an equatorial electron group. In the trigonal bipyramidal electron group geometry, lone pairs are always equatorial. So there we go. Now we have two purple connectors representing lone pairs. They still are part of the electron group geometry. They contribute to the molecular shape, but now we have a T-shaped molecule. So again, trigonal bipyramidal electron group geometry, but T-shaped molecular shape. All right, one more. There's another view of it, I guess. So now we replace the third equatorial position, or that third equatorial position is a lone pair, and we now have 5 electron groups, 3 of which are lone pairs, 2 of which are bonds, and the molecular shape now is linear. Okay, last is the octahedral molecular shape, or octahedral electron group geometry. If all of the electron groups are bonds to atoms, then this is an octahedral, both electron group geometry and molecular shape. But, and so we can see kind of views of it. Another view. And now, if one of those lone pairs, or sorry, one of those electron groups is a lone pair, again represented by the purple connector, we have a square pyramid for our molecular shape. So that lone pair contributes to that's part of the electron group geometry, but the electron group geometry is octahedral, the actual molecular shape is square pyramid. Okay, next place that the electron group would be an electron group that's a lone pair rather than a bond pair will end up being opposite side of the molecule from the other lone pair, so that one. So now we have 2 lone pairs, top and bottom in this sense, so we have a square, and it's flat, it's a planar. So this is a square planar molecular shape, but it's an octahedral electron group geometry. One more. So now we have 3 electron groups that are lone pairs, 3 electron groups that are bond groups. That makes a T-shape, and we still have an octahedral electron group geometry. Okay, one more replacement, or one more lone pair. There it goes. So now we have 4 lone pairs, 2 bond pairs, linear molecule. Okay, so here is a summary, and this is on the handout, and there's plenty of references for this. So this is just kind of a reference. 2 electron groups, 3 electron groups, 4 electron groups, 5 electron groups, and 6 electron groups. 2 electron groups, linear is your only option if you have atoms bonded to the central atom. 3 electron groups, atoms, all places, makes trigonal planar, but if one of the electron groups is lone pair, we have a bent molecular shape. 4 electron groups, tetrahedral, if they're all bonds to atoms. One of them is a lone pair, trigonal pyramid. 2 of them are lone pairs, bent or angular. 5 electron groups, all bonds to atoms, trigonal bipyramid. 1's a lone pair, sawhorse. 2 are lone pairs, T-shape. 3 are lone pairs, linear. And octahedral, all 6 electron groups are bonds to atoms. That's an octahedral molecular shape. One of them's a lone pair. It's a square pyramid molecular shape. 2 are lone pairs. It's square planar. 3 are lone pairs, T-shape. And 4 are lone pairs, linear. Practice is good with these and getting the names, shapes, geometries, all that stuff straight. Okay, one more thing. Now we're going to deal with molecular polarity, and we'll use some molecules we've seen before. So here is a molecular model of CO2, carbon in the middle, double bonded to oxygen on either side. The Lewis structure is shown below that. And note there are 2 electron groups. The double bonds count as each double bond counts as a group. So they're on opposite sides of the molecule, so it's a linear molecule. And you've previously seen some information about bond polarity. Oxygen's more electronegative than carbon, so the oxygen to carbon bond is a polar bond. The dipole points towards the more electronegative atom oxygen, and so this side of the carbon-oxygen bond is a little bit negatively charged, and this side's a little positively charged. Now there's a second carbon-oxygen double bond, so that also has a dipole. This oxygen, or this end of the dipole, is a little bit negatively charged. This is a little positively charged. So we have two bonds between carbon and oxygen. Both are polar bonds, so both have formed dipoles, but they point in opposite directions, so those bond dipoles cancel. And in this sort of molecular tug-of-war, since those bond dipoles cancel, the overall molecule is non-polar. There's not one side that's negative and the other side that's positive. It's a symmetric cancellation of the bond dipoles. Now let's contrast that to OF2. And here's a model of OF2. Here is a Lewis structure. Oxygen has two bonds to fluorine and two lone pairs, so it makes a bent molecular shape. Fluorine's more electronegative than oxygen, so there is a bond dipole from oxygen towards fluorine. Fluorine's a little bit more negative, oxygen's a little more positive. And same for the other oxygen-fluorine bond. And now, because of the bent molecular shape, because of these two lone pairs, these two dipoles do not point in opposite directions, and they do not cancel each other out. And when they add up, they actually make a net dipole, or an overall dipole, that's pointing towards the fluorines. So the fluorine side of the molecule is a little more negatively charged. Relatively speaking, the oxygen end of the molecule is a little more positively charged. And since the bond dipoles don't cancel, since there's an overall or a net dipole for the molecule, we say the molecule is polar. All right, let's take a look at CCl4, molecular model, tetrahedral shape, Lewis structure, carbon with 4 bonds to chlorine atoms. And in that tetrahedral shape, we have a carbon to chlorine bond 4 times. Chlorine's more electronegative than carbon, so the bond dipole points towards the chlorine. So does this one, so does that one, and so does that one. And in three-dimensional space, a tetrahedral molecule with bond dipoles that are all the same, pointing to the 4 corners of the tetrahedron, those 4 dipoles, those bond dipoles, all cancel each other out. It's a three-dimensional tug-of-war, if you will, and no one side of the tug-of-war has a stronger pull than any other, so those dipoles cancel. The molecule is overall non-polar. There's no net dipole. And one more example, SF4. Here is a molecular model. Here is a Lewis structure. Sulfur has 4 bonds to fluorine atoms and a lone pair, so it has a seesaw or sawhorse structure. Fluorine's more electronegative than sulfur, so bond dipole from sulfur to each of the fluorines. And the 2 axial fluorines have their dipoles cancel, but the 2 equatorial fluorines also have an equatorial lone pair, and those dipoles do not cancel. And since those dipoles don't cancel, there's a net dipole towards the 2 equatorial fluorines, and there's a net overall dipole, means that the molecule overall is polar. So this side's a little bit more negative, those equatorial fluorines. This side's a little bit more positive, and the molecule overall is polar. All right, so that is it for Molecular Geometry Part 2 and an introduction to polarity.